Triple integrals. In this section, we'll be covering triple integrals that are just an extension of the double integrals. You'll notice that there's a lot of similarities. So it's basically the same basic procedure as we did with double integrals, but of course there are some slight differences. Now, by analogy, the definition of a double integral, we define a triple integral as a similar idea, but this time it's the limit of triple Riemann sums. So something like this. And just like back in 15.2, we also had Fubini's theorem. In this case, we have Fubini's theorem for triple integrals, which shows you that if you have constant limits, notice how you have constant limits for all three of these integrals. You can actually integrate these in any order you want. Now, it's not always going to be that easy, because if your integrals have limits that are not constants, then you will not be able to integrate them in whatever order you please. So you're going to have to be careful. But whenever your triple integrals have all three limits are constants, then you have yourself a situation where you can actually integrate these however you wish. Notice in this particular case, the differential dx is closest to this integral here. So a and b are x values. I know I'm repeating myself, but I hope you're understanding. The middle differential dy here corresponds to the middle integral here. So c and d here are y values. And z here, the differential z is the furthermost outermost differential, which corresponds to the outermost integral. So therefore r and s are the limits for z. So having said that, let's go ahead and take a look at an example where all three integrals are actually constants. So we take a look here. Let's say we're integrating over this region E. Now this is no longer a region. One thing I really want to point out is that triple integrals do increase the level of complexity a little bit. And one way they increase the level of complexity is that a double integral integrates over a shadow. Basically, think of a beach canopy casting a shadow to the ground on the beach. That shadow on the ground is what you're integrating over. Well, when it comes to integrating triple integrals, we are no longer integrating over a shadow or a two-dimensional area on the ground. We're actually integrating an entire solid. And in this case, this is a rectangular prism. This rectangular prism has a distance of a width of 2, a length of 3, and a height of 2. So we're actually integrating over not just an area on the ground, but we're integrating over an entire solid, which is actually kind of hard for a lot of our minds to fathom. Another thing I want to point out, as I just want to mention, is notice that we're taking a triple integral of some function. Whenever that happens, you're going beyond volume. We're going into a region known as hypervolumes, and we'll talk more about that later. But right now, I just want to kind of just start with the basics here. Again, because all three limits of each of the variables here are all constants, we can actually integrate this however we wish. So for example, if I go ahead and start with z, make this a type 1 situation. Basically, I start with integrating by z, but just make sure that your first integral on the inside are my z values. In this case, z goes from -1 to 1. So therefore, that's why these limits here are in the innermost integral. The middle integral is y, which is why my middle integral is from -3 to 0. And my outermost integral is going to obviously be my x values, which go from 0 to 2. And I can kind of just reveal the other two ways that we can actually do these. Here's where we actually start with x's, then y, then z. And here's one where we do first y, then x, then z. And of course, we could actually even do a fourth one where we have z in the middle. So there's actually 4 different combinations here that we could possibly do. And you'd get the same answer all 3 shots. Now, this one actually is not that hard to integrate. So feel free to go ahead and integrate this yourself if you wish. And you should get the same answer all 3 times. But why don't we go ahead and take a look at an integral here that, a triple integral I should say, where we can't necessarily use Fubini's theorem. without doing some major changing of order. And by the way, you can change the order of even an integral like this. However, it does take some thought and some potential, sketching, like little sketches and sometimes some little geometry. But here, this is pretty straightforward. I mean, it's the same basic procedure as double integrals. So I'm just going to kind of fly through this one. Notice here we are integrating with respect to z first. So I am going to skip a few steps, and I would like you to pause the video and try to bridge that gap between my steps that I skip. For example, in this case, I will just kind of verbally say what happens here. Since I'm integrating with respect to z first, and there's no z in the expression in the integrand, I'm going to end up with 2xyz. And we're going from 0 to x plus y. And because of that, I end up getting you might notice, well, where did the x and the y and the z go? Well, again, I'm kind of skipping some steps here. This becomes xyz, and then where you see the z, you plug in x plus y. So imagine that in this little expression here, there was a 2xyz here, but you'll notice that you don't see a z here. It's because I already plugged in the x plus y for that z. So again, I would ask you to pause it here, do the middle step here, and try to bridge the gap. If you still can't see how I got from here to here, again, please email me. I am more than happy to send back to you the intermediate steps if needed. Then now, of course, we're going to go ahead and integrate with respect to y. So obviously this becomes 1/2 y squared, and that half will cancel out with this 2. This is going to become 1/3 y cubed. So obviously this one I did not skip a step. This one I actually went ahead and showed you the middle step here. So again, this is 1/2 y squared. The 1/2 cancels with the 2, and this becomes 1/3 y cubed, and the 2x just kind of came down. Now this 2x and this x, you're going to plug it in. Now this is where students get, they mess up. There's so many variables and so many moving parts that students often lose track of what they're supposed to actually be doing. Well, in this particular case, remember, these are y values. So you're supposed to plug these two guys right here. In fact, let me go and show you here. You're supposed to plug in this value here and this value here wherever you see a y, not the x. You leave the x alone for now. And once you do that, you plug those in. First you plug in 2x both into y squared and y cubed, and then you subtract this x value here that you plug into y squared and y cubed. So using fundamental theorem of calculus part 2, you ultimately end up with 23 over 3x to the 4th. Once again, please pause the video here and try to do this yourself. Please get from here to this step here, okay? And then obviously this last step is just basic calculus 1, and hopefully you also get 23 over 15. Okay, let's try another example. Here we're going to integrate with respect to y first, and again I'm going to skip a little step here. Since I'm integrating with respect to y and there's already a factor of y in the integrand, this is going to become 1/2 y squared with a z hanging out off to the side. But I'm going to go ahead and plug in the x right away anyway, and then you subtract 0, so that's kind of, you can just ignore that, and you end up with this. So I said to you a second ago that this here becomes 1/2 y squared. And here you don't see 1/2 y squared, you see 1/2 x squared. That's because I went ahead and used fundamental theorem of calculus part 2 and plugged in the x right away. And then obviously you're subtracting 1/2 0 squared, which just cancels out, goes away. And now we're going to integrate with respect to z, so this z becomes 1/2 z squared. Now here I'll go ahead and show the middle step. Here's 1/2 z squared. The 1/2 times this 1/2 becomes 1/4, and obviously I have my z squared here. What's nice about this is that I'm going to go ahead and take this radical, the quantity 9 minus x squared. I'm going to plug it into z, yes, and in this case it's being squared. So this square is going to cancel out the radical here. And then of course I'm going to go ahead and minus the 0. That's going to be of no consequence, so I'm just going to ignore the 0. And I'm going to kind of kill two birds with one stone. So again, z squared with this being squared is going to just become a 9 minus x squared. And then you'll notice I'm going to go ahead and distribute the x squared, and that gives me 9x squared minus x to the fourth, which again becomes calculus 1. You should end up with 162 over 5. Once again, please pause your video, try this yourself. Do not brainlessly write all this down and just think, oh, okay, I can do this myself. I can figure this out myself later. No, please pause the video, bridge those gaps. Again, email me with a timestamp. Let me know if you still need help. Many times, though, I will ask you to send me what you have so far. So I do want to see at least some effort on your part to try to bridge the gaps here that I'm skipping. But if you aren't seeing how I bridge those gaps after you tried it honestly, then go ahead and send me an email with a timestamp, and I will help you, no problem. Now, earlier I mentioned that there are 3 different ways we can use Fubini's theorem if you have all your limits are constants. But what if not all your limits are constants? Like in this example here, you'll notice that I can't just switch things around like I wanted to from the previous example. So like if I go back up a little bit, if I go here, notice I have 3 different ways of integrating because all my limits are constants. Well, that's known as Fubini's theorem. However, with these next 2 examples that I just did, you won't be able to do that without a bunch of intuition and some geometry and sometimes a little bit of dumb luck. And also here, you're not really able to switch the order of integration without some serious work. So whenever this happens, whenever you have integration or triple integrals where some of the limits are variables like that, you're going to have to categorize them into different types. Let's go ahead and start with type 1. Now, what makes a solid region to be known as a type 1 region? Now, I'm going to go ahead and show you a bunch of mathematical jargon, and then I'm going to break it down to piece by piece. Basically, a solid is type 1 if your x and y are essentially limits of just straight up constants, and your z can only be expressed in terms of functions like x and y, x and y. And if you're kind of thinking, I don't really understand what that means quite yet, well, it's okay. Basically, what I'm trying to say is that d is the projection of E onto the xy plane. And I end up getting this situation here where if I'm trying to evaluate a triple integral here, okay, and here's the thing though, what if I notice though that my z values are strictly in terms of some variables, but my x and y variables are strictly in terms of constants? Well, another way to put it, it looks something like this, okay? Now notice, what really makes this type 1 is the following. It's just simply because I'm going to go ahead and take the integral with respect to z first. It really doesn't matter if I do dx dy or dy dx. However, if I do dy dx, then your second set of limits must be functions of x. But if I flip these around, these must be functions of y. But it would still be considered, again, still would be considered a type 1, mainly because you are taking the integral with respect to z first. Now, types 2 and 3 are similarly defined. So I'm just going to go ahead and show you everything from the book. So notice that a type 2, you start with, you integrate with x with respect to x first. And then the dA in this case is going to be either dz dy or dy dz. And then finally, a type 3 is when you actually start by integrating with respect to y, which means in this case, your dA is either dx dz or dz dx. And if you're wondering, well, which one is it? Is it dx dz or dz dx? Well, again, it depends on the problem that you're given. Depends on the situation that they throw your way. But once again, as a recap, if you're integrating with respect to z first, that's type 1. If you're integrating with respect to x, that's known as type 2. If you're integrating with respect to y first, that's known as type 3. And you'll get better and better at these as you progress. Again, sometimes you will be able to switch around the order by using a little bit of intuition, some geometry, maybe even a little sketch. And the beauty part of all this is that you actually, many times, it doesn't really matter which type you use. And many times, a lot of these solids that you're presented with can be actually solved using type 1 or type 2 or type 2 or type 3 or sometimes even all three. So why don't we go ahead and evaluate an integral. Now, I'll show you later how sketching a graph of the solid does help a lot, but sometimes it's really hard to do unless someone graphs it for you. Because these are not just typical quadratic surfaces typically. Now sometimes they are, and if they do give you a quadratic surface as a solid, then you should be very happy about that because you guys are pretty good at quadratic surfaces by now. But many times you just kind of have to look at these and use your intuition. Now notice that this one is interesting. So this one I have my z or my constant. So this definitely will not be type 1. It's not type 1. So this is either type 2 or type 3. But upon further inspection, notice how y can be written in terms of z and its upper limit, but x also can be written in terms of z and its upper limit. Because they're both written in terms of z and their upper limits, these are actually both type 2 or type 3. So what I'm going to do is I'm going to go ahead and show you how to do this using type 2. What I highly, highly, highly recommend you do is redo this problem yourself as a type 3. And if you do this as a type 3 and get the same answer as me, then you're on your way of figuring out how to do a triple integral early on in the early stages. So I'll do a type 2. So go back to your earlier notes. What constitutes a type 2? A type 2 means that you're going to be integrating with respect to x first. Okay, that's all that means. So what comes after dx? Is it dy dz or dz dy? Well, in this case, it's very clear. If I do x first, I have to do y next. Because since z are my constant terms, you want to save that for last. You want to save the best for last. It's like what I did with my double integrals last class, was that you want to get rid of the more complicated limits first. So if I get rid of the x limits first, I got to get rid of the y limits next. So in this particular case, it's got to be dx first, then dy, then lastly dz. And you'll notice that is reflected in our limits with the integrals as well. Hopefully by now that makes perfect sense to you. Now this is a pretty easy integration, so I honestly don't think, I think at this point you probably know exactly how to solve this, but I'll just kind of quickly go through it. Since I'm integrating with respect to x first, obviously my antiderivative here will be just simply x. And then you're going to take this z plus 2 and plug it in for x. So that's how I got the z plus 2 here. And then, of course, we can disregard the 0. Now we're going to integrate with respect to y. So this y becomes 1/2 y squared. Notice again, I skipped a step again, didn't I? Actually, I skipped a few steps. This becomes 1/2 y squared. But then you're wondering where all this came from. Well, basically, I took 1/2 y squared. I plugged in 2z. I got 2z cubed, and then I took 2z cubed and distributed throughout these two terms inside. And again, disregard the 0. And then finally, we're just integrating term by term with respect to z. And since I just have this simple limits, this is just simple power rule from Calc 1. And try to get 7/5 also. And again, please, I cannot emphasize this enough. Please do type 3. I know some of you are looking at this going, yeah, I got it. But nothing beats actually practicing and writing this out yourself and actually getting to that answer from scratch. Now, here's where it gets interesting because this time they're just basically, basically describing E in practically nothing but words. In the last example, at least they had it kind of laid out in a set formation. But here, they are essentially just um, telling you what the solid E is in words. Let's use our common sense here. So, for example, we want to be under the plane. That's very important. Under this plane, that means this is going to be an upper limit of some point. So if we're under the plane z equals x plus 2y, that means we're under this guy, which means this has to be some sort of upper limit. But it's also above the region in the xy plane. That's the floor, that's the ground, bounded by these curves here. Okay? So trying to draw that is going to be really hard to do. And you're welcome to try, but you would have to draw it in 3-dimension, and it does get kind of tough. Okay? However, I want to point something out. I just told you that this here is going to be an upper limit because we are under this guy, right? UL means upper limit. And notice here that z is in terms of both, not just x, but both x and y. And I told you guys, we're supposed to get rid of our most complicated limits. Well, notice that down here, y is in terms of x, and here y is just 0, and here x is just 1. So my most complicated limit here is this upper limit in terms of x and y. So that tells me I'm going to want to integrate with respect to z first. I'm going to want to get a dz out of this somehow. Okay? And go ahead back to your notes from the previous slides. When you're integrating with respect to z first, that is known as a type 1 triple integral. And to me, there's almost no other way of doing this other than doing some serious geometric rearranging. And so because of that, and again, we're starting at the ground floor. Remember, if you start at the ground floor here, this is actually really important. This comes up a lot. The xy plane, please don't forget, is equivalent to saying just simply z equals 0. So this will be my lower limit going up to my upper limit of z equals x plus 2y. So as you can see here in my integral, my lower limit is 0, which is z equals 0, and my upper limit is the plane that I just described previously. And once again, notice that dz is inside. It's the first differential. And again, we're starting at the floor and we're going up to this parabola. Okay? And then finally, with my x values at the end here, we're starting again at 0 and going up to a maximum height of 1 for x. Now we go ahead and integrate this. There's no z in my integrand, so my antiderivative is just going to be z times y. And then I'm going to replace the z with the x plus 2y. And I went ahead and took the liberty of distributing the y at the same time. So I ended up getting this here. So again, pause the video. Try to get this yourself by doing the intermediate steps. Now we're going to integrate with respect to y. So this here becomes 1/2 y squared x. This here becomes 2/3 y cubed, which I went ahead and showed the middle step there. Please remember that this is a y value. This means y equals x squared. This down below means y equals 0. These are y values. So you're going to replace every y that you see with this guy. And when you do that, you end up with this. So actually that is the intermediate step. I literally plug an x squared into here. The x to the 4th times x is x to the 5th. Plug in x squared here. X squared to the 3rd power is x to the 6th. This should make perfect sense to you. Then of course, final answer, I'm just going to go ahead and give it to you because now it becomes a super easy calculus 1 problem. Now this one's actually interesting. I actually like this one a lot. So to me, this is kind of a fun problem. And to me, this really reveals how to actually establish your limits on your triple integrals. Please understand, in this section, finding the integration and the antiderivatives is not going to be hard. In fact, it's no harder than what you did in the double integrals with the occasional, you might have to do trig sub here and there or partial fraction decomposition or whatever. But other than that, the integration is not really that hard. It's the setup that's hard. That takes some getting used to. Trying to understand how the limits work. So to me, the best way to actually solve a problem like this is that if you can actually find a way to sketch first, then please do. Sometimes sketches are really hard to do, but if you can find a way, trust me, it's worth the hassle. Because if you don't try to attempt to sketch what's going on here, then trying to find your limits is harder to do, and you sometimes you'll just get lucky and maybe get it right, but other times you completely fall flat in your face. So I'm gonna go ahead and sketch this, and I'm gonna show you what I have for a sketch, and then explain to you how I got this sketch in the first place. So this little pyramid here is exactly what is being described. And how I know this is because you can start with the easy stuff. So like x is equal to 0. Well, that's this plane over here. That's basically where this y plane here. Okay, this zy plane, I should say. That's going to be x equals 0. Okay. And then y equals 0 is going to be exactly that. It's when y equals 0. It's basically this. It's this plane here. This plane here that's going along the x-axis and going up and down the z-axis. That is going to be y equals 0. It's basically the xz plane. We've talked about that before. And finally, we've already spoken about this in this very lesson. Z equals 0. Well, that's the floor, right? That's this guy. Okay. And because of that, I want to show you. I mean, like that. Those first three equations show you how we get this triangle in the back, this triangle on the left, and this like square on the floor, rectangle or square, whatever. But how did this become a square? Because the bottom floor, z equals 0, is not it's not a perfect square. This is a perfect square though, because what we do next is we go ahead and we take these two equations here, and we basically set them equal to each other and try to solve for them in various ways. And by doing so, that's going to actually create this line here and create this line here. And you're going to create this dot here. And it's also going to help you discover the intersection between those two triangle planes there. So that takes some getting used to. And to sketch that, it just takes a little bit of intuition, a little bit of patience. So again, if you just go ahead and, for example, solve for z here, solve for z here, and then set them equal to each other, that's going to help you find those intersections. In fact, you set z equal to each other in both of these, you will get that line. In fact, more specifically, if you set z equal to each other, you end up getting this line down here, which helps you give you this diagonal. So to me, this is not a very difficult solid to sketch. So I would recommend that you pause the video here and try to sketch this yourself. I know you got to see it yourself in plain sight, but I would actually ask you to try to sketch this yourself. And one other tip is what I would recommend is try to find out how to plot these points here. Is what I would actually kind of point out. In fact, maybe I should have mentioned that first. Try plotting those points first and just connect the dots essentially. Now that you had some time to try to sketch this thing yourself, I want to go ahead and start integrating this thing. Now, as I mentioned before, the triple integral itself is not difficult. To integrate this thing is a breeze now. It's just a little bit more challenging than a double integral. And as you saw, a lot of double integrals are quite simple once the integral is set up. It's the setup and finding the limits that is kind of difficult. Now, one kind of nice thing about this particular situation is that you'll notice that actually this is a kind of a symmetrical figure here. So I'm going to actually use that to my advantage, and you'll see why in a moment. Because our goal is, in this case, is to try to find the volume of this thing. Well, I should say this is actually a hypervolume, I should say. This is not a true volume problem. We'll get to that later in the class, and possibly in the next section. But in this case, because symmetry can be very helpful in this case, I'm going to go ahead and remove that line there. So you see, I'm going to remove that line, and I'm going to focus only on this little mini triangle over here off to the left-hand side here. So let's go ahead and we're just going to integrate this solid here. So this solid consists of this triangle face and this triangle bottom all the way down to the origin here. It's that little pyramid there. So basically, we're going to stop it at this wall here. This triangle wall is going to be kind of like our boundary. And if right now you're thinking like, what is going on? I don't understand some of this stuff. It's okay. It's going to take a while for us to wrap our heads around it. But I do want to let you know that I can go into more detail if you wish as far as graphing this. But I do want you to try to start sketching it yourself. I gave you a little bit of a preview of it here. So let's go ahead and integrate this thing. So how do we integrate this? Well, let's take a look at the fact that we have symmetry. One thing I will kind of mention though is when it comes to R3 figures, when it comes to three-dimensional figures, and later on when we get to what are known as hypersolids or hypervolumes, symmetry is almost useless. But in very basic cases, symmetry does work. And again, I'll be explaining this more in detail later. But for now, luckily for us in this particular problem, symmetry does actually work. And again, you'll notice that it works in this case because I took away that line here. And before I took away that line, this whole solid here was consisted of two of these smaller pyramids. So go ahead, here's a bigger version of it. Now, what's interesting about this particular problem is that I'm going to go ahead and make this a type 1 triple integral. But what's nice about this one, what's very interesting, is that you actually can do this one as a type 2 or a type 3. So because of that, I want to go ahead and kind of point out that because it's a type 1 situation, follow my lead and just go ahead and see how I actually do this one. But if you actually can go back and try this as a type 2 and a type 3 and get the same answer as me, then you really are going to know how to do a triple integral, and more importantly, you're going to know how to set up the triple integral limits, which is the hardest part of this section. And furthermore, to really emphasize my point, as we move forward into the semester, what you're witnessing now with the triple integrals is essentially I'm paving the path for the rest of the semester. And if you don't understand how to set up limits for triple integrals, it's going to be kind of a rough road for a couple weeks until you really get that solid foundation under you of how to set up triple integral limits. Again, the integration itself will not be hard. It's the setting up of the limits that you're going to have to be careful with. So actually, to show you how to do this problem, what I feel is best is to just go ahead and give you the triple integral right away with all the limits and everything. Now you might think, well, why are you giving us all the answers now right away? Well, I'm giving them to you now so you can kind of not only see what is the appropriate setup for a triple integral of this nature, of type 1, I should say in this case, but also I'm going to go ahead and step by step show you how I constructed it. Now let's go ahead and start. Now again, I told you that symmetry works, right? So in this particular case, symmetry does work. but you have to be very careful when it comes to three-dimensional figures. But because in this case symmetry works, you'll notice I have a factor of 2 here because we are utilizing symmetry, because we have to consider the fact that my original solid E here was not just this smaller pyramid, it was actually double this. So hopefully that makes sense. Okay, here we go. Let's do it. So what I want to do is I want to show you guys, I'm first going to start with integrating with respect to z. And obviously you can see that. We all know that I'll be integrating with respect to z first here. And you'll see this vertical line here. Now, whenever you integrate with respect to any variable, x, y, or z, remember, you are always, ever since even Calculus 1 days, you're always integrating from a smaller value of your variable to a larger. You're always going from smaller to larger. You're going from smaller value of x to a bigger value of x, from a to b, or from c to d, or whatever. But you're always going in the direction of whatever axis you're following. So in this case, since I'm integrating with respect to z first, what's happening here is I'm actually going to just go ahead and integrate going straight up, and I'm going to just pretend like it's like an arrow. Okay, so pretend we're shooting an arrow into the bottom of that figure there, and notice how it's entering this floor through the xy plane right here. Okay, it's entering through the floor here. Now that point just happens to be there. It could have been anywhere within this little triangle here, but the point is it's entering through this floor here on the xy plane. And since it's the xy plane, well then that obviously is going to be z equals 0. And that's why that's my lower limit to start us off. So hopefully that's not too bad. But then again, you're shooting an arrow through this thing, okay? And the arrow is just going straight up through that point. And because it's going straight up through that point, it's not going up to this little corner over here. It's actually exiting somewhere on the triangle here. Now, it's kind of hard to see. But basically you're going through the bottom, through that triangle, into the middle of this solid, and coming out at this point here physically on the triangle itself. So you see this arrow coming up here above, where the arrowhead's up here. This arrowhead is physically outside of the pyramid. So it's inside the pyramid between these 2 points and then comes out here. But you'll notice it's actually hitting this triangle here, isn't it? Well, this triangle happens to be the plane z equals 1 minus x. And how did I know that? Well, it's on the previous page. The previous page, you'll notice that one of the planes was in fact x plus z equals 1. If I were to add x on both sides, I'd get x plus z equals 1, correct? So if you were to go back to one slide before, you would see that this is actually one of my planes that this solid's being bounded by. And obviously it's being exited, it's an upper limit, so I go ahead and put that as my upper limit on my integral here. So once again, the arrow is being shot, hitting the bottom, getting me a 0 lower limit here, exiting through the plane itself, and this plane happens to be 1 minus x. Okay, now that the z is taken care of, how did I get the next limit? How did I get the limit with respect to x this time? So again, whenever you're going in the direction of your integration, you're always going from least to greatest in that direction of the axis. So we first started off with a z-axis going just straight up. So what about the x-axis? Okay, well the x-axis is going to be this. Notice that I'm going to shoot another arrow this way. And notice that this arrow here is parallel to my positive x-axis. That is no coincidence. That's no accident. And I'm going to shoot this arrow, but there's something that happens that's quite special. And this is actually very important to consider. I'm going to shoot the arrow, but this time, this arrow is going to go through the triangle again, but notice that I'm only shooting this arrow strictly on the floor. Now, you might wonder what's that all about? Well, because I already took care of my z-axis, this solid has now collapsed from a 3-dimensional solid into a 2-dimensional triangle on the ground. I'll say that one more time. we started off with a three-dimensional solid. And after I took care of the z-axis, this solid collapsed into the ground to become just that triangle you see on the floor, and that's it. We no longer concern ourselves with the entire solid. We've already taken care of it through the use of integrating z. So as I shoot my arrow, I am now shooting my arrow on the ground. This arrow is traveling on the floor, and it's hitting this dotted line here, okay, entering at this point. Well, as you can see here, I'll point it out here. That line on the ground there is the line x equals y. If you were to connect these dots from here to here, that is physically the line x equals y. So because of that, my lower limit here is y. Now, why am I saying that it's x equals y and I'm saying my lower limit here is y and not x? Well, keep in mind, guys, that these two limits here, this middle integral, these are x values. So this little flashing circle is indicating that that down there is x minus y. So I'm going to let that equal to y down here. And then I'll get to in a second, this upper limit here is x equals 1, which I'll get to in a second. You'll see why that is in a moment. These are x values, so you must solve for x, and specifically, so this has to be y down here. So once again, we're shooting our arrow. It's hitting this dotted line here, okay? And as you might already guess, let me go ahead and erase this first. As you might already guess, the arrow is continuing on and shooting out and hitting this solid line at this edge of this triangle. Now notice we're still on the floor, aren't we? So because we're still on the floor, we are looking at just simply the line x equals 1, which again corresponds to my upper limit here. So let's go ahead and move on to the final step here, which is integrating with respect to y. Now this is even easier. It's obviously the easiest one of all. And I'm going to go ahead and just kind of circle all the elements that we need to see. Now, before I actually specifically tell you how I got from 0 to 1, remember this first started out as a three-dimensional solid. And after I took care of one of the dimensions, it became a two-dimensional shape. So you can kind of imagine what happens next. It goes from a three-dimensional solid, this three-dimensional pyramid, collapses down to a two-dimensional triangle on the floor, and that now collapses down to a one-dimensional line here. Okay? And once again, since we are integrating with respect to y, we're going to be going in the positive y direction, and notice coincidentally that this dark solid line here happens to be parallel to my y-axis. And the smallest y value on this line is 0, right here. And the largest y value on this line is 1. That's why we go from 0 to 1. So as a recap, you start off with a three-dimensional figure. We integrate that. We shoot the arrow through the bottom of this floor and up into this side little triangle coming out of the solid. That collapses down to the triangle on the floor. That collapses down to this solid line here, which I will highlight. Just kind of collapses down to this line here. Okay. Now, the next step is quite simple. Because now that we have the integral set up, integration at this point should be a breeze. So I'm going to go ahead and have that typed out there for you again. And I almost should just kind of skip this because you've done several of these already. So I'll just go very quickly through this. Obviously, we are integrating with respect to z first. So this is going to become 1/2 z squared. The 1/2 cancels with the 2. I simply square the upper limit of my z values here. Again, this upper limit here is an upper z value limit, okay? And that ends up giving me the 1/2 cancels with this 2. I just end up with 1 minus x quantity squared. Pause the video. Please try to get to that point yourself. Now we integrate with respect to x. Well, again, this is a pretty basic integral to integrate with respect to x, because I end up with this. Now I went ahead and showed you the intermediate step here. This negative actually comes out because of the chain rule factor, but then the rest becomes pretty basic. It's just the argument to the cube power divided by 3. And then now we plug in a 1 here. That's going to give me actually 0. So actually we can almost disregard. And then we're going to subtract this entire thing, but replacing this x with a y, which gives me this. And then finally, you integrate this with respect to y. And that's very simple because this is just simply going to be, you can expand this using Pascal's triangle and then integrate it term by term or however you wish to do this. And you should end up with 1/12. So really the hardest part about this, once again, I cannot emphasize this enough, is not the integration, as you can see here. The integration is easy. It's the setting up of the limits that you're going to have to get really good at. And I highly recommend that you go in your book and on top of the homework that I assign for you online, you should also go in the book and do all of the odd problems where they're asking you to set up the actual limits yourself. And practice, practice, practice. You cannot get enough practice of that. Because figuring out how to set up these guys right here is the key right here. So please make sure you do that over and over and over again. Now there are several applications of triple integrals. There are so many different ways that you can interpret take a triple integral and interpret it in different ways with different physical situations. So I'm not really going to go too deep into that. But I do want to point this out, though. Notice that this here is having us find a volume. And it's very similar to what we did in the last section when I told you guys how if you ever take a double integral of just dA, well, the answer to that is just the area of whatever region you're dealing with, that whatever shadow is on the ground. Well, in similar fashion, if you take the triple integral of dV, and again, notice how here I don't have an integrand other than the number 1. So that's just 1 multiplied by dV. Whenever you have this situation, but this time it's a triple integral of 1 times dV, well, that simply is just going to be the volume of whatever solid you're dealing with. So that, in fact, does find the volume for you. So let me back up a little bit to the previous problem. So let's just kind of, we'll see what happens here. But notice in this last problem here, it's not quite what I'm explaining now. Notice that here we actually do have a little something extra here, don't we? That's not 1, that's the letter Z. And if you have anything extra, anything at all, other than 1, this is now known as a hypervolume. This actually goes beyond 3-dimension into 4-dimension and actually is quite impossible to visualize and even impossible for a computer to really graphically show you how what that looks like. Now, there's definitely ways a computer can numerically analyze and give you an idea of what how it behaves and the outcome of a hyper volume. But if you have anything extra in the integrand besides 1, and you take the triple integral of that, that is a hyper volume, and that's when you're starting to dive into like 4-dimensional apparatus. So let me back up here. This is the picture that we got from this last example, and I mentioned that we were looking for what's known as a hypervolume. Well, basically, this is what I mean. What I mean is we're only integrating over this entire solid. So the answer that I got out of this from the I think it was 1/12, that value of 1/12 is associated with a hypervolume. It's a volume that's even greater than what's going on here and more complex than what's going on here. So in front of us we see a pyramid, but that 1/12 represents something so much more than just the volume of this pyramid. So it's quite a fascinating concept to try to wrap your head around. So just kind of put that in perspective, okay? If you have something extra in the integrand besides 1, it becomes a hypervolume. Now, going back here, once again, as I showed you earlier, because I have a 1 in my integrand, this is just going to be whatever the volume is of the solid that we're dealing with is going to be the answer to this particular problem. So let's go and look at an example. Okay. Now I went ahead and took the liberty of just giving you the sketch of this right away. And I would highly, highly, highly recommend that you try to sketch this yourself by hand. It's pretty hard to do, but you can do it if you just have a little bit of practice and patience. But look at the question. It's asking us to find the volume of the given solid. So because it's asking for the volume of the given solid, your integrand must be 1 for this next problem. So the next problem will definitely have this going on. It's going to have 1 dV going on, and that will not be the hard part. Again, the hard part will be finding the limits, but I'll explain that right now. So like I said, once again, try to sketch this yourself. I would recommend that you start with the elliptic cylinder. That should not be hard for you to sketch because we sketched these back in chapter 12 and probably even earlier than that from other courses. Notice that I have no value of y, so you'll notice that you can just draw a cylinder that is going in the positive and negative y direction, but it's obviously being cut off here by the plane y equals 0, because y equals 0 represents this little circle on the back end here. So that's cutting that off, right? And then this here, this plane y equals z plus 2 is literally just the line y equals z plus 2 cutting across into the x-axis, and that's represented by this guy here. Now to graph this thing, again, I think it's pretty easy for you to graph the cylinder and to cut it off here at the base where y equals 0. The hard part will be here, and what makes it easier is knowing where that these two intersect. So if you simply take this point right here and just set these two equal to each other, you'll see that z equals -2. So you'll find out what this point exactly is. This point is going to be the point. It's going to be the point 0, 2, -2, basically. So that's pretty easy to find once you set these equal to each other. And then, find the intersection here now. So how do you find this intersection here? You find it by setting these two equal to each other. So you set this equal to this, somehow. I would personally solve for z and then plug that into here and then try to find your way there. That's one way to do it. But sketching this out yourself by hand is going to be a crucial skill. So please do that, and please practice that religiously and make sure you get good at that, because that's going to be a very important thing. Because take a look at this next slide here. This is what you should do to properly set up the integral. Now to me, this is a type 3 situation. This is a type 3 integral. And there might be ways of doing it differently, maybe like type 1. I think type 2 might be a little tough, but again, with some little algebraic gymnastics, maybe you can get to a type 2. But this here is a type 1, and again, once again, as promised, I did tell you that check out the integrand here. The integrand is in fact 1, because we are looking for the volume of this thing. So let's get to the question of how I got this here. Now, me personally, again, we're going to shoot an arrow. If I shoot an arrow, coming from the back end here, again, we're integrating with respect to y first, right? So we're going to start from negative y values out to positive y values. So we're going to want to draw an arrow somewhere over here in the negative y region and shoot it this way, and make sure that it's just parallel to the y-axis. It's going to hit that circle somewhere in this region here, okay? And it's going to hit this circle, right? And I just told you earlier, what is that circle? That circle is the back end where y equals 0. So that's how I got this lower limit here, okay? And then that arrow continues to shoot through and keep shooting through until it hits the plane on this end and then shoots out of the solid itself. Well, what does it hit before it comes out? It hits this circle, which again, it's right here as clear as day. That's your plane, y equals z plus 2, which is why that becomes my upper limit. Again, these are both y values. So y equals 0, y equals z plus 2. Now, remember, this three-dimensional figure is now going to collapse into two-dimensional. Now, in the previous example, you recall when it was three-dimension, I integrated with respect to z first, and it collapsed down to the floor, down to the xy axis. Well, this time I'm integrating with respect to y first. So because I'm integrating with respect to y first, this thing's going to collapse in the y direction now. So it's actually going to collapse. This whole solid here is going to collapse down here to just this circle that's collapsing down to where y is just nothing. Just like in the last example where z collapsed down to the floor, which is the plane z equals 0, this solid is going to collapse down to this circle here where y equals 0. And since I'm integrating with respect to z, we're going to start in the negative z region and shoot an arrow straight up into this circle. It's going to hit the circle here. This is the lowest spot that it's going to hit. And it's going to continue through straight up, 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 up until it hits this end of the circle and exits out the other end. So this will be my lower limit here, and this will be my upper limit here. So how I got these guys? Well, again, where did I get this circle from? This circle came from the elliptic cylinder. And if you simply, again, these are, since I'm integrating with respect to z, both this lower limit here is a z value, and this upper limit here is also a z value. So these are both values of z. So what you basically do is you just simply take this guy and you solve for z. If you solve for z, then you ultimately get these limits here. So once again, we're shooting an arrow in the positive z direction. It enters here, this lower half of the circle. So again, if you solve for z here, obviously I'll take the square root, which will give me the positive negative version of these. Again, you'll subtract 4x squared. You get 4 minus 4x squared inside of a square root. So obviously this lower limit here would be the negative radical quantity 4 minus 4x squared. And then shooting out to the other end here would be the positive radical quantity 4 minus 4x squared. So again, as a recap, we started with y. We integrated with respect to the y, went in the positive y direction. This three-dimensional solid got collapsed down to the two-dimensional circle. And now that we got the two-dimensional circle out of the way, this two-dimensional circle now collapses down to my one-dimensional line here. Now I apologize, actually, now that I think about it. This magenta pink line here could have been anywhere on the circle. I just happened to draw it on the z-axis. I apologize about that. That could have been actually drawn anywhere. But now we're collapsing down to this single line that's physically on the x-axis itself. And as we can see here, the smallest x can possibly be is -1. And the largest this x value can be here is +1. Okay, and how do I know that? All you simply have to do there is this blue line here, guys, is not only true. This blue line here is not only true on the y equals 0 plane, but it's also, if you actually notice, it's also on the floor, which means z also equals 0. So to figure out the values for x, all you simply have to do is, once again, take this relationship here and replace z with 0. Solve for x, you'll get plus or minus 1. Now, once again, this problem here requires some thought, requires some skill. Again, I'll repeat myself. Note that we were using a triple integral to find volume, so notice that the integrand is 1. The hard part is not the integrand being 1. The hard part is finding these limits. Now, integrating it is a breeze. Once again, you'll notice that we can actually utilize symmetry here again, but please be careful. Symmetry is not always very useful in three-dimensional situations, so please be careful, especially with hypervolume. It's definitely a dangerous place to be. But whenever you can use it, go ahead. It does sometimes make your life a little easier. Notice that my limits are all basically the same, but instead of integrating from -1 to 1, I'm integrating my x from 0 to 1. In fact, if I go back, you'll notice if I'm only integrating from 0 to 1, I'm integrating the half that's on our side in the first octant and below. And then obviously multiplying that volume by 2, you'll get the back half. Now we're integrating with respect to y first. So my antiderivative of dy is just simply y. And I'm integrating from 0 to z plus 2. So obviously I'll just get z plus 2. Now we're going to integrate with respect to z, which is simple. We get, this will become 1/2 z squared. This will become 2z. And we're going to plug in these guys. So here's my intermediate step. So how I got here is at this last step that, if you'll notice, how you integrate this. And by the way, again, if I were you, I would pause the video, plug in these values. You're going to see a bunch of stuff cancel out, and you should end up with this. Now, to me, this last step going into the final moments here is you're going to need trig sub for this, or a table, which gives us this. And then, of course, we are integrating from 0 to 1 this time, which would give us 4 pi. So let's go ahead and use a triple integral to find the volume of the given solid. The solid is going to be enclosed by these two paraboloids. Now, I think without even graphing it, it's pretty easy to see that z equals x squared plus y squared opens upward, and z equals 18 minus x squared minus y squared opens downward, based on our previous experience with quadratic surfaces. And also the paraboloids will intersect. Now that's going to be important because, and I'll draw a quick little picture in a moment, but this one's going to open upward, and it starts lower than this one that opens upward, or excuse me, downward. And that they intersect when you simply set them equal to each other. So if you set x squared plus y squared equal to 18 minus x squared minus y squared, and then if you go ahead and add x squared plus y squared to both sides, divide by 2, it's pretty easy to see algebraically that we end up getting that they intersect at x squared plus y squared equals 9, which we all know is the circle x squared plus y squared equals 9 is a circle of radius 3. Now students might think, oh, that circle must intersect at z equals 0. Not necessarily. This is actually a cylinder, It is a circle, but it's a circle if it was only 2 dimensions. But because z is missing, this is actually a cylinder that goes up and down forever with a radius of 3. So if I, so basically we're going to end up getting the following region that we'll be integrating over. Pretty complicated looking, but don't panic too much. So again, this here is a cylinder of radius 3, which you won't actually see in the actual picture. It's just simply where they intersect each other, and z is bounded by the first paraboloid that was listed below and the second paraboloid that was listed above, and that's going to be hovering over z. So I'll go ahead and draw like a quick picture before I get into this. The first paraboloid, as I said, is a paraboloid that opens upward. This would be a really terrible picture, so you guys will be able to draw it better on yourselves. It's like a bowl-shaped figure that opens up, like a paraboloid here. Bowl-shaped figure that opens up is the first paraboloid that was listed. And then there was another paraboloid that is opening downward, and they intersect at that circle there. Now that circle is a circle that is basically part of the cylinder I was talking about from the previous page. But we get this like egg-shaped figure here. Okay, and as I said, they intersect in this little circle here. They don't just intersect on the circle. They also intersect on, actually what I should say is the disc. So this entire disc that I'm shading in green here is where they intersect. My picture is pretty terrible, but it still gives you kind of the idea. So as I said, first let's take a look. Now I want to really point this out. Now we're going to go ahead and try something clever here. We're going to actually try to utilize polar coordinates. And the reason why is because you'll notice already, you've seen it like 3 or 4 times already in this problem alone, that the expression x squared plus y squared has popped up a couple times. I mean, the first paraboloid is strictly just that. The second paraboloid, if you factor out a negative, you get an x squared plus y squared in the expression. And then if you set them equal to each other and solve for x squared plus y squared, it pops up again. Well, we all know this to be, the famous r squared formula from polar coordinates, right? So you can see that this would be a great candidate for polar coordinates. And many times I won't tell you, when you integrate these things, I won't tell you, hey, use polar coordinates. You'll have to just recognize, hey, I think I can use polar coordinates. And many times, if you can see that you can use polar coordinates, then do so, because it's just going to make your life so much easier. So moving on, we're going to go ahead and integrate this. We're going to find the volume. So as I've mentioned before, because we're going to find the volume, remember, volume with using a triple integral means triple integral with an integrand of simply 1. Okay, so we'll be finding the volume of this thing, and this thing being the solid, that's the E. We are this basically is just a fancy way of saying we'll be integrating over the solid E. And again, a 1 times dV just means we're finding the volume of E. Now the clever way to do it is this. We're going to go ahead and follow the same things that we did before, where we're going to go ahead and integrate with respect to either x, y, or z. Now in this particular case, I believe this is a type 1 situation. It's a type 1 situation to me, because if you take a look here, how this picture is situated, if I shoot an arrow from a negative y region you know, and I shoot the arrow and I hit this top part of the shell, well, the problem is that if I shoot an arrow in the y direction, positive y direction, I should say, I'm sorry, it's going to hit a different shell down here. So then I'm going to have to do two different triple integrals. We don't want that, right? And then the same thing with x. If I decided to integrate with respect to x first, you're gonna have to come from this angle. You know, you're gonna hit the top shell at a certain point and come out the top shell. But then again, you'll have to do a second triple integral if you want to do the bottom part of the shell and find that solid. So again, doing dx or dy first, trying to do type 2 or type 3 first is possible. And it might be a good challenge for you if you're bored or if you need something extra to do. Feel free to try to solve this thing doing a type 2 and a type 3. But to me, this is type 1 because, again, if I did type 2 here with the x route, basically coming from the negative x region, going towards the positive x direction, I'm going to hit this top shelf, come out this top shelf, then I have to do a second triple integral to get the volume of the bottom shell. We don't want that. So to me, it's a type 1 situation because if I go ahead and draw a z arrow, again, remember what I did with that first problem where I used a type 1. If I draw an arrow from the negative z direction going in the positive z direction, so again, let's draw our arrow. It's going up, 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 and what's happening? It's going to hit this bottom shell somewhere, and it can hit the bottom shell anywhere, really. You know, you can go here, you can go over here, you can go over here. It doesn't really matter where you start, but the point is just kind of pick some random area on this bottom part of the shell, and it's going to hit the solid down here. It's going to travel inside the solid, so I'll do some dotted lines, okay? And then it's going to exit the top shell, so probably around here somewhere, which to me justifies it being a type 1 because no matter where I shoot the arrow from the bottom, it's going to hit that bottom shell to enter the solid and exit through the top shell no matter what, all within this little green disc here. So again, this first part actually should make some sense because notice I shot the arrow up. Now you might be wondering, like, this looks a little weird. You haven't seen this before, right? I get it. Don't panic yet. But you'll see that I shot the arrow, hit the bottom shell, traveled within. So again, so it hits the bottom shell. That's this guy, right? And then it exits the top shell, which makes it my upper limit. So if you really are following me in this whole shooting an arrow type thing, this should make sense to you. And of course, we're integrating with respect to z. So that's why, you know, I have this set up the way it is. And again, don't forget the integrand started off as just 1. Now this should be very easy to integrate. It looks complicated, it looks crazy, but it should be very easy to integrate because the antiderivative of z is just simply, the antiderivative of dz is simply z. So if I take the antiderivative, I get z, and then you're just simply plugging in the upper limit into here for z, subtract the lower limit. So it's essentially just going to be 18 minus x squared minus y squared minus, using fundamental theorem of calculus part 2, minus this lower limit here. And the point is, we end up getting our next step, which is going to be simply this. So I would pause the video here, and you should be able to get this yourself. Once again, my antiderivative here is going to simply be z. You plug in the upper limit minus the lower limit, and you know, algebraically clean it up. You should get this. Pause the video. Please try this yourself. And this is where the polar coordinates really shine. If I simply factor out a -2, okay, you're going to see we get x squared plus y squared, right? But please don't forget what happens. We have just integrated with respect to z here. So as I've said before, I'll say again, This is a three-dimensional solid figure, right? So after I integrate with respect to z, this three-dimensional solid figure is going to collapse. Well, collapse into what? It's going to collapse into that disk of intersection that we saw earlier. So you see this little disk here. I'll just draw it again. It's going to collapse. Here it is. And I apologize, but it should be the same size. So that same disk I was discussing earlier, we now are dealing with just that disk now. Okay, so that disk that was in this original picture is now this guy here. So that's what we're dealing with now. We are now integrating over that region D. This is the region D here. Okay, so all we really have to do is find the area of that thing, but we have to find the area of that thing including a beach canopy. This is actually like, now it becomes basically section 15.3, where we're going to be integrating over this region using this beach canopy here. And again, like I said, this is where the polar coordinates really shine, because I factor out a -2 from both these here, okay? And I end up getting -2r squared, which should be a pretty easy conversion for you. And then, of course, dA becomes r dr d theta, not just r dr d theta, but excuse me, not just dr d theta, but with the r in front of it. Don't forget that. And what's the area of this disk? Well, I think we all know it's going to be a radius of 0 to 3 from the origin out to a radius of 3, the max. And then we rotate all the way around 360 degrees. So if I wanted to be literal, if I wanted to fly over this disk and look at it from a bird's eye view, it's going to be like a perfect circle. That's actually not too bad of a circle. Here's my disk once again, but this is us at a bird's eye view flying over the thing. This is a disk of radius 3. So its smallest radius it could possibly be is 0. Its biggest radius it could possibly be is 3. And of course we are rotating all the way around this 360 degrees, which gives us the 2 pi. And then of course at this point it's a very easy integral to integrate, so I almost don't think I even have to do it for you, because I just simply distribute this r inside and then I power rule this thing. And we end up with this here. And then of course this is a super easy integral, because you'll notice that r is just a constant. So out of that I just end up getting a constant, and you just multiply this thing by 2 pi. You end up getting 81 pi out of it. Okay. Now this next portion is just from the book, so you can kind of just take a look at it. It's a bunch of formulas that are applications of triple integrals. They have actually many more in the book, so please feel free to read it. So I'm just going to quickly go over this and not really delve too much into detail. But some other applications of triple integrals are basically like, finding what's known as a density function. Basically, you can actually find the mass of a solid if you know its density. If you know the density of the solid, let's say you're trying to find the mass of a solid that, let's say that previous solid, that picture I drew in the previous slide, let's say it was made of gold. Well, we all know what the density of gold is. It's been scientifically proven what's its density, or the density of ice, or whatever the solid may be. If you simply put its density function in a triple integral, you can not only find obviously its volume, but by taking this guy out, but by putting this density function in, you can actually find its mass as well. And you can also, based on things that we learned back in Calculus 2, you can also find their moments. And that's really important because since you can find their moments, you can actually find the center of mass in the solid as well. So let's say the solid was uniform density throughout the entire solid, but let's say it was kind of irregularly shaped. Like let's say, like in the last problem, the top half was like a little bit bigger than the bottom part. Well then, chances are the center of mass, or the centroid, is going to be a little higher. It's not going to be right down at the origin. And you can use these formulas to figure those out. And then, of course, we have moments of inertia, which, again, we learned back in Calculus 2. And they're just basic formulas here. So let me back up real quick. If you know the density function, and usually, many times it's just given to you, then which is nice. But basically, you can actually find the center of its mass using these formulas here. So if I back up one more time, the mass itself is going to be the triple integral of the density function dv, and you'll have to set up the limits of integration, which does take some practice. Once you do that, again, as you noticed, once we got the integration or the triple integral set up, it was actually a very simple integration situation. So the integration is not the hard part. It's setting up the triple integral that we need to practice. But again, here are some formulas for the mass, the moments. Here's the center of mass formulas. You simply divide the moment, in this case, the moment about the YZ plane divided by the mass. To find the Y coordinate of this centroid, you take the moment about the XZ plane divided by the mass, and the center of mass at the coordinate Z, you take the moment about the XY plane divided by the mass. Okay, so basically this here, they look simple, but they're actually, this is a triple integral divided by a triple integral. Here, inertia, here's some extra formulas for you to see. And I could potentially ask about these on the next exam, so please make sure you know these formulas. I'm debating whether or not to put the formulas on the test itself, so please make sure you memorize them just to make sure that you have them. And let's go ahead and do it. Let's go ahead and do an example. So I'm going to go ahead and find the mass. Let's start with finding the mass. The mass of this paraboloid here. Then we'll do the center of mass. Then we'll do the moment of inertia about the z-axis. So I will go ahead and first start by looking at the mass of this paraboloid. So the mass is going to follow that formula I showed from the previous few slides. And it would be a good idea to draw the picture. So what does this picture look like? Well, based on our experience from paraboloids from previous chapters, this should be pretty easy for us to graph. But notice that this is not a typical paraboloid. The last example, the paraboloid was about the z-axis, so it opened up and down. Notice here that this parabola is not about the z-axis. This parabola is going to be actually about the x-axis. So if I went ahead and drew this, and just bear with me, I'm going to draw this as slowly as I can. I have my little xyz axis. This here is a paraboloid that opens in the positive x direction. So from the origin here, I'm going to open it up outward towards the positive x direction here. Okay. And this thing does go on forever, but the solid specifically does not go on forever. It is actually capped off by this plane x equals 4. Which, if you were to take x equals 4 and set it equal to this parabola, x equals 4y squared plus 4z squared, it's going to intersect at this disk here. It's going to cap it off. Sorry, that's supposed to be a perfect oval or a perfect circle, but I think you get the idea. And just like the other problem, or very similar, it's intersecting at a disk here, and that's going to be very important momentarily. So again, it's a paraboloid that opens in the positive x direction, and it's capped off by the disk x equals 4. Well, it's actually a plane that goes on forever, but that's their intersection, is that disk there. Now, this one's really nice because, again, I really want you guys to get good at setting up your limits. That's the hardest part about section 15.6. So in this particular case, this to me, the best way to solve this one would be a type 2 situation. Now this is type 2 because if I, again, shoot my arrow, type 2 means I'm going to integrate with respect to x first. So if I shoot my arrow in the positive x direction, coming from the negative x region, it's going to enter the parabola first, right? It's going to hit the parabola first, dotted line inside the parabola, inside the paraboloid, excuse me, and then it's going to exit somewhere on the other side through that little disk x equals 4, come out the other end. So the lower limit is going to be the paraboloid itself. The upper limit is going to be the disk. And we're going to integrate with respect to x first. So let's go ahead and reveal what the triple integral looks like. Hopefully this makes sense. Now this problem is a little bit different because we are not looking for volume this time. So because we're not looking for volume, you'll notice I actually put the density function into the integrand as asked for in the previous few slides. Here's my density function here. Here's rho dx, dz, dy. Now I'm going to do dx first. Now actually this one's nice because after I get dx done, you could do dy dz or dz dy. It doesn't really matter. So I would actually ask you guys to try this problem yourself and switch the dy and the dz and see what you get. It's going to be pretty much the same idea. But recall, this is a three-dimensional solid figure. And again, because I'm integrating with respect to x, we are coming from the negative x direction. We're coming from that area, but we're heading toward the positive x axis, hitting the paraboloid first. So that means that's going to be right here, my lower limit, right here. And then it's going through the solid, exiting out, and hitting the upper limit of 4. And once that's accomplished, once that's all said and done, remember, this three-dimensional figure collapses, right? It collapses into a two-dimensional figure. So once that's taken care of, it collapses into a two-dimensional figure. Basically, it collapses into this disk here. And if I were to kind of like stand on the x-axis itself, we'd end up getting a disk. Here's again the disk. Sorry, it's kind of a bad picture. So it collapses down, and we're coming from the positive x direction. We're looking from the positive x direction backward. So having said that, essentially this disk here becomes, like I said, two-dimensional. Sorry, it should be centered. But this is the y-axis, and this is the z-axis. So now we can shoot an arrow from the negative y to the positive y direction, or the negative z to the positive z direction. Either way, notice how I'm next going with dz, right? So what I'm going to do is I'm going to be shooting an arrow. Since I'm going to do dz next, I'll be shooting an arrow from below. It's going to hit the disk. Now here it's just going to hit the disk right at the border. But notice how I'm let me make that a little nicer. Okay, I'm going to hit the disk here right at the border. Okay, it's going to travel inside the disk straight up. It's going to hit the disk at that top region. And again, I could have shot this arrow anywhere. I could have shot it over here. You know, I could have shot it over here. I could have shot it over here. I decided to shoot it here. It doesn't really matter, but it hits the bottom half of the disk, travels through the disk, and exits out the other end like that. So you'll notice that my lower limit is going to be this guy. That's the lower half of this circle. And if you're wondering, well, how do I get that circle? Well, again, this is represented by the intersection of the paraboloid and the plane, right? So it's this circle here. So basically, again, as I mentioned earlier, if you take this paraboloid and set it equal to this plane, basically replace x with 4, you'll get that circle. And then what you do is you simply solve for z, because again, these here are z values. These here are z values. If you solve for z, you'll end up, and we've done this earlier in this lesson. My lower limit is the lower half of the circle, which is here. So again, we're entering the lower half of the circle here, which is this guy, and exiting the upper half of the circle, which is this guy here. And then finally, once we finish the 2-dimension, it collapses into a 1-dimension, which finally gives us, you know, basically our integration with respect to y. Which is going to be this guy here. So this 2-dimensional figure is going to collapse down to just simply the y-axis. And you'll notice in the y-axis, you just simply, we're going from -1 out to +1 for my y values. These here are y values. Okay? So very consistent though. And it's going to take a while for you to get your head wrapped around this process. But and now this problem just says to set up but don't evaluate. But the setup, like I said, is the hard part. Now that we have it set up, I believe you should be able to integrate this yourself. Okay, so once again, just as a little reminder, I'm going to erase this for you. The way we get those second limits is you set 4 equal to 4y squared plus z squared. And then you can get the second limits that way. For parts B and C, I'm just going to go ahead and give you the answers right now. It's literally just following the formulas. So my center of mass here is going to be following the formula for x bar. And it's really just simply you tacking on an extra x there, if you guys see that. It's simply x times the density function itself. And you'll notice that the limits are exactly the same for not only x bar, but y bar and z bar. And they're all being divided by 1 over the mass. Well, what's 1 over the mass? 1 over the mass is what we got in the previous section. So this is mass right here. This is my mass. So whatever you get from this crazy triple integral, it's going to follow you into these triple integrals where you're just simply going to divide every single one of these by whatever you got in your answer from part A. And then do yet another crazy triple integral. And it looks pretty intimidating at first, but like I said, the hard part is not the integration. It's the setup of the limits, which we already did from the previous page. And same thing with inertia about the z-axis in this case. Same limits, notice that. And again, you're just, the inertia about the z-axis just tacks on an extra factor of x squared plus y squared, as you'll follow in the formulas. So that's one application of triple integrals. There are many, many more. In fact, the book talks about them. One being an electric charge is a very um, uh, useful application, and also something known as the joint density function is also going to be something that can be useful, among many more. Finding average values. There's so many things that you can do with triple integrals. Now, as I mentioned in class, and I'll mention again here, triple integrals is kind of a weird one. It's a weird section. It's a weird topic, and understanding how to set up the limits is the key. So please be patient. Please watch my video several times if you can to really get a true understanding of how to set up the limits. But also feel free to look at other videos as well to see if those work for you also. But don't forget that I will be emphasizing my videos on my exams. So I still do expect you to watch my videos in their entirety. And if you have any questions, again, timestamp your questions for specific parts of the video, and I'm more than welcome and more than happy to send you intermediate steps, or maybe even set up some sort of online meeting where we could talk and chat and get things done that way as well.